Alright, this is a video for exponential functions, which is going to be section 3.1. This is only going to be the first part of the section though. And these notes are going to go on pages 70 and 71 of your notebook. Okay, so hopefully this is going to be review from Algebra 2. And what we're looking at is exponential functions. So let's start by sort of defining what an exponential function is. So an exponential function is going to be anything of the form f of x equals sum a times b to the x. So the thing that really identifies it as an exponential function is your variable x is the exponent. So there are some important things that have to go along with this function, such as the a. The a value cannot be 0, otherwise you don't have a function anymore. That would just cancel everything out. The b value must be greater than 0, so it can't be 0 either. In other words, it can't be negative. And the other thing is that b cannot equal 1. Because if you think about it, if you have a 1 here, no matter what value of x is here, you're just going to get the same thing. It's going to be a line, basically, which isn't what an exponential function should be. So there are different types of exponential functions. We have the growth exponential functions, and it's considered growth if the b value is greater than 1. And then we have the decay. Now, we already discussed how b has to be greater than 0, but if it's less than 1, in other words, between 0 and 1, it is a decay function. So visually what that means is, well, let's pop open Desmos and play with it a little bit. Okay, so I've set it up so that we have y equals a times b to the x. And a I want to keep positive for right now, but it can be negative. And b I've set it to be from 1.1 to 10. So by the definition that we just talked about, that would make it a growth function since I'm making the b values greater than 1. So if we push play on that, you can see what that b value does to the shape. It's almost so fast right there, it's like a whiplash, but we could slow it down a little bit right here. Right, and I set it to be 1.1 and not 1 because if it is equal to 1, like we said, it is a perfectly straight line. So we don't want it to be that, and Desmos doesn't allow us to just say strictly greater than or strictly less than. So I had to change it to just, I could do 1.01, that would be fine. If it's 1.01, it's probably it's barely indistinguishable from a line, although if you keep looking at it as we pull it, you can see it's not a line. It is increasing, it is growing. And if I zoom out, you can see it definitely does look like the other ones eventually. Maybe not when we're zoomed in at this level. It doesn't look like a growth function. But if we go ahead and push play, even right now, I had said it's so slow, we only have 1.5968 as our b value. It gets very steep very quick with such a barely larger than value of 1b. Okay, and if we play around with a little bit, you can kind of see there's something going on here. It kind of looks like it's being pulled up. We know from our understanding of transformations that the value of a, if it's greater than 1, which it is right now, will do a vertical stretch, which is what's happening. But if I pause it, if you look at this point right here, which is our y-intercept, that y-intercept of 6.36 is the value of a. And a major reason for that is the x value was 0. And when we plug in 0 as an exponent in this setup right here, you're going to get a times 1 because anything to the 0 power is 1. And a times 1 would just give you whatever the a value is. So this simple function that we have going, this basic exponential function, you could say the y-intercept is always going to be whatever the a value is. And so I'm going to write that down as something we want to include in our notes here. There's a point, a very easy point. If we plug in 0, we will always get a, and that is because a times b to the 0 power will always be a times 1, which is just a. Okay, going back to our graph, there's another important point there. And let's see if we can use decimals to find it. Oops. There we go. It's the point 1 comma AB, which is this point right here. Notice as I drag this point, it's changing the value of either A or, in this case, B. 9.22 is what you get when you multiply A times B. So the reason that this is happening is when we plug in 1, anything to the first power is just that number, so you just get the product of A times B. So that is another important point of exponential functions. When we plug in the number 1, we get A times B as our output. And then you could plug in other numbers, right? You can plug in 2, you would get A times B, whatever B squared is. It is important to remember order of operations, exponents before multiplication. So when we stick numbers in here, let's say A is 3 and B is 2, your function would be something like this. This is not equivalent to 6 to the x power, okay? Because you cannot multiply 3 times 2 because the exponent is attached to that 2. It's like it's trapped there, okay? So those are the growth ones. I want to compare that to the decay ones. So let's go back and look at a decay one. So maybe for this one, I'm going to change the b value so that it is between 0 and 1. I don't want it to equal 0, so I'm going to make it 0.01 because I have to, it forces me to have an equals there. And it has to be less than 1, so I'm just going to write it as 0.999 or something. Okay, did I get that decimal point in there? Yeah, okay. So if we push that, you're going to get a very different graph. Let's make this point go away. Here we have decay. And so each of these different functions have some applications which we'll look at in class this week in the next part of the section. But essentially decay is just what it sounds like. Something is decaying over time, such as radioactive decay, or population decay, or something that is decreasing over time. And you can see when I have a b value of something really tiny, like 0.01, it's going to decay at a very sharp rate, compared to if I have something that's almost 1 at 0.99, it's decaying at a fairly slow rate. If you think of it in terms of like percentages, 0.999 as a percentage is almost 1, right? So it's almost, if I said like, okay, after one day we have 0.99, or we have 99.9% left. So not much is gone. Versus if I have 0.3, then that means 30% left. Okay. All right, so let's just sketch a little graph of these. If it's growth, you're going to be starting here and going up. Now, another thing that we need to talk about is the fact that these have horizontal asymptotes. And the horizontal asymptote comes in right here. It's the x-axis, or the line y equals 0 is our horizontal asymptote. And that is because there's no value of x that I can plug in here that would give me 0. Right? If I have, let's go back to the 3 times 2 to the x, for example. 3 times 2 to this. Is there something that would make this 0? If I plug in 0, I get a 1, and that doesn't work. If I try plugging in negative values, such as -5, I get 3 times 1 over 2 to the 5th power, or 3 over 32, which is getting to be a very small number. That's not 0, but it's getting tiny. Now, what if I did a 50 here? Then that would be 2 to the 50th down here, which would be a much larger number in the denominator, which would make this overall thing much, much smaller. So if we look at this specific example, let's just make this go away. Let's just type the one I'm describing, 3 times 2 to the x. Okay, so if we find -50 in the x, okay, it says 0 right now, but we discussed this at the beginning of this semester. Desmos does have a potential for graph error. If we really zoom in, we can actually start to see that it's not 0. It's just approximating it to be equal to 0. Let's see where we're at. It still thinks it's 0. We're going to have to zoom in for a day or two probably, but eventually we'll see it's not actually 0. What if I do this? Oh, that's much faster. Okay, once you're getting into scientific notation, then it's getting a little better. Oh, okay. We have something as the y value that is not 0 at this point. All right, we're getting 3 times 10 to the -15th power, which means we would move the decimal to the left from the 3 15 times. So we're talking minuscule, but we're not talking 0. And that's important because there's no possible way to get a 0 out of that function. And so it creates this horizontal asymptote at y equals 0. And that was true for the decay functions as well. But the decay functions start high and then start to approach the asymptote from the other direction. That's pretty much the difference, but it still has this asymptote right here. Okay, at the very beginning of I think it was like chapter 1, we talked about the 12 basic functions, and we had one very important exponential function, and that was the function f of x equals e to the x. And e to the e, this number e, you may remember, is a constant. It's about 2.718. It's an irrational number, kind of like pi is. And e comes from a limit, okay? It's called the natural base. And I linked a video in your checklist this week for some really interesting applications of E that you may not have seen before. We'll look at least the interest ones on our next class, but let's talk about where E comes from. Okay, E is the limit as x goes to infinity of the following: 1 plus 1 over x to the x power, all to the x power. Okay, so I'm going to get a calculator and I'm going to show you what I'm talking about. Okay, so what I'm going to do is I'm just going to calculate this expression. I'm just going to start at 10 and then maybe go to, up by powers of multiples of, so we have 10, 100, 1,000, 10,000. Okay, so we're talking about 1 plus 1 plus 1 over 10, all being taken to the 10th power. Okay, so 1 plus 1 divided by 10, so 1 and a tenth, all being taken to the 10th power, we get 2.5937. So approximately 2.5937. Okay, remember this is E. So if we keep going, you can go ahead and pause the video if you'd like to try this yourself. Just get out a calculator and do the rest of them, and then you're going to watch to see how this number is changing as we go higher and higher and higher. And when you're ready, unpause the video. Okay, so if you do the next three, it goes from 2.5937 to 2.7048 to 2.7169 to 2.7181. You see you're getting closer and closer to the actual value of E. Remember, there is an E button, so this is what I was getting in the last one, 2.7181459, whatever. If I push the E button, that's the actual value of E. So you can see exactly how close it's getting. And so we definitely have a very important number on our hands here. Okay. So moving on, we have a basic function of e to the x, but we also are just going to talk about how we can manipulate this one a little bit. So we have an exponential function with the base e. We want to write it in the form that we started with a times b to the x, but instead of b we have e, and instead of just x we're going to have a kx. Alright, now the k value could be a number that is positive or negative. So let's think about if it's negative. Like, what if k was a negative 1? Okay, a e to the negative x, for example. What does that negative do to the function? Well, it's like a negative 1 right here. So it's like it's taking e to the negative 1 power. And e to the negative 1 power would be 1 over e. So this is equivalent to a times 1 over e to the x. Now 1 over e is basically 1 divided by that 2.718 number, right? If we do 1 divided by e, you get this number. This number would make it a decay function because it is a number less than 1. While e on its own is a growth function because it is greater than 1. Okay, so if we have that negative is actually telling us that we have a decay function. And it could be any negative number. If it's negative 2, then that means we have 1 over e squared, which is still going to be a number that is less than 1 and therefore decay. So the general rules for this one are if a is greater than 0, so a is positive, we're still kind of leaving a positive here, and k is greater than 0, all right, then you have a growth function. And alternatively, if a is greater than 0, so this is staying the same here, but you have that k is less than 0, in other words, you have a negative k, that's going to create a decay function. So the reason we're leaving the a as a positive number is if we look at the graph. Let's go back to Desmos for a minute. Oh boy, we've got to zoom way back in, don't we? You know what we can do? We could just That's going to take like 10 minutes. Let's just go to Desmos again and launch the calculator, and it's all brand new. Okay, so if we have a value that is negatives, because I restricted that the first time. Right now b is 1. We don't want that to happen. Let's a be negative. That's what happens. It's going to flip it upside down, as it does with any function. If we make the put a negative in front of it, it's going to flip it upside down. And so that's not really how growth and decay work when we model them. And so that's why we're kind of ignoring that for right now. Okay, so that's all I wanted to do for this video, is just give you kind of a reminder of exponential functions in E, and we'll look at logistic functions in class. Okay?